Last week, we talked a lot about the photoelectric effect. In fact, we've talked about it this week as well, just not quite as much. The photoelectric effect says, in essence, we'll summarize it here, we'll paraphrase the photoelectric effect, says when light strikes a metal, an electron is sometimes ejected. If that electron receives enough energy from the photon, then the electron will be ejected. If it doesn't receive enough energy from the photon, then it won't be ejected. If we want it to be ejected, we've got to increase the frequency of the photon, not the intensity of the photon, not the number of photons, but rather the frequency of the photon, the type of EMR, so that we get a higher energy corresponding to the possibility that the electron will be ejected. If we up the frequency even further, to not just a little bit above the minimum or threshold frequency, but way above the minimum or threshold frequency, then the electrons will still be ejected in a 1-to-1 ratio. 1 electron for 1 photon, 1,000 electrons for 1,000 photons. But those electrons will be more energetic. Today we want to talk about, and yesterday we also talked about this, we want to talk about the Compton effect. The Compton effect, similar to the photoelectric effect. Light strikes a metal, you got a photon, that causes an electron to be ejected, just like in the photoelectric effect. But if that photon is of sufficient energy, like maybe an X-ray photon, and an X-ray photon is a really, really high energy photon, then it's not just an electron that's ejected, but sometimes a second photon is ejected as well. It doesn't happen with the photoelectric effect. Now, that second photon, it was observed, was a less energetic photon than the first photon. Classical theory, and we talk about classical theory as being old-style physics, before quantum theory, before this idea of photon theory, and the energy of the light is related to the frequency. Classical theory would have predicted that the photon that was ejected over here would have been the exact same energy, the exact same photon as the first photon that struck it. There's no reason why light can change. Red light is not going to change into infrared. Ultraviolet is not going to change into blue light, according to classical theory. But classical theory didn't match with the observations that were made. The observations that were made said that, yeah, the second photon is less energetic than the first photon. It is a smaller frequency than the first photon. Okay, now we enter Compton, another guy with quantum theory, with photon theory. Einstein, we kind of say, is the first. Okay, Compton, okay, another guy shortly thereafter. I believe the year was 1908. Compton said the way that we explain this is to explain it as a collision between a photon and an electron. The photon strikes the electron is scattered at an angle, and then the electron is kicked out as well. It's kind of like maybe you got a car sitting at an intersection, a truck hits the car, and then the truck and the car both scatter off. The truck having less energy than it did when it first hit the car, right? When it struck the car in the first place. That make sense? So when a truck hits a car, a stationary car, the car goes off at whatever speed, the truck gets scattered as well, but the truck is less energetic than it was when it struck the car to begin with. It's like a collision at an intersection. But if it's like a collision at an intersection, then the law of conservation of momentum must apply. And if the law of conservation of momentum applies, then all of these things, the photon, electron, and the second less energetic photon, all must have momentum. This is one of the big takeaways from the Compton effect, is that photons have momentum. And that's kind of hard to understand at first because photons don't have any mass. If you don't have any mass, then how can you have momentum? Well, we derived 2 equations yesterday. We won't re-derive them, but I'll just write them down. They appear on your data sheet. We derived 2 equations for the momentum of a photon. The first one related the momentum of the photon to the energy of the photon. E is equal to P times C. The second one related the momentum of the photon to the wavelength. P is equal to H over lambda. And those came about through this whole equation from Einstein, the energy mass equivalence formula, which, unless you're deriving those 2 equations, you don't really need to use in this context. E is equal to P times C. P is equal to H over lambda for the momentum of a photon, something without mass. Now, this thing up here, P equals mv that we learned back in Unit 1, this still applies, but it only applies to something with mass, with matter. An electron, a baseball, a proton, a photon bottom, proton top, without mass, with mass. Got it? Now, we also learned another equation yesterday that we didn't even attempt to derive. The second equation that we learned was delta lambda. And remember, if the energy of the photon is changing, then the wavelength is changing as well. If the energy goes down, then the wavelength will go. Who can answer that question for me? If the energy of the photon goes down, and it does, then the wavelength of the photon will go up. So delta lambda, a positive value, it's going to increase in wavelength, is equal to h over mc times 1 minus cosine theta. H is Planck's constant. It has two values, but we're always going to use one particular value for this. Which one's it going to be? 4.14 or 6.63? 6.63 times 10 to the minus 34 joule seconds. In fact, that's the value that we're going to use for everything involving the Compton effect, the 6.63 value. It's starting to get confusing, right, as to when we can use 4.14 and when we can't. If you're confused, then use 6.63. Always use joules. Okay? If you understand when you can use joules, when you can use electron volts, then do whatever. But if you're confused by that, then just always use that value. M is the mass of the electron, C is the speed of light. Theta is the scattering angle. The scattering angle of what? The electron or the photon? Cool? Right, the scattering angle of the photon. Got it? All right. We did two sets of problems yesterday. The first one had 3 questions with it, page 723. Any issues with any of those 3 questions before we move on? They're all good? Okay, the second set of questions, in fact, there was only one of them on the second set, page 724. Any issues with that question on 724? Nope? All right, we'll do one more example then, and we'll be finished this topic. This one is on page 723. It says, what is the maximum change in wavelength that a 0.010 nanometer X-ray, that's going to be our initial wavelength. I want to circle nanometers here. What's the maximum change in wavelength that it can undergo by Compton scattering with an electron? Does the initial wavelength matter here? Guys, look at this. We're looking for the maximum change. We have the initial value, and that's it. Where should we start? If you think about this, everybody should be able to come up with a starting point. You may not be able to finish this question. It's a tricky question. But everybody should be able to come up with something to start with. Who wants to volunteer that for me? What do you say, Prager? EF minus EI. Okay, if you do, that's perfectly valid. Okay, anytime you tell me something that's perfectly valid, okay, I'm going to say go for it. Okay, now in the end, if you do that, you're going to go HC over lambda, F minus HC over lambda I. You have lambda I, you have H, you have C, you don't know what lambda F is, right? And you don't know what delta lambda is, or delta E is, or delta lambda. So it doesn't look like that's going to work for me. Okay, but bottom line is it's not going to get you a wrong answer, right? Anytime you try something valid, it's either going to get you the answer or it's not going to get you an answer. It's not going to get you the wrong answer. So never shy away from trying something like that. Never. It's valid. Try it. Doesn't work. Okay, let's try something else. Somebody else. Mark says P is equal to H over lambda. Is that a valid equation here? Absolutely it is. Absolutely. So we're going to say maybe Pi is equal to H over lambda I, because you have the initial wavelength. Okay, we got this, we got this. We could solve for the initial momentum of the photon, right? Not sure that's going to help me, but it's not wrong. Okay, that is the initial wavelength of the photon. Good. It's just, in this case, I don't think going to be helpful to me. Anybody else? Right, it says E is equal to hc over lambda. I think we're going to find a pretty similar situation to what we found with Mark's suggestion there. Okay, we can solve for this, but it doesn't really do anything for me here to find the maximum change in wavelength. Is anybody thinking the one equation that we have that directly allows me to solve for delta lambda? Did that occur to anybody? Now, somebody's going to say, like, oh, yeah, okay, that kind of makes sense. We're solving for a delta lambda. Like, let's use the delta lambda equation, but, oh, wait, how are we going to find delta lambda max from that equation? Well, in the end, there's four variables in that equation, h, m, c, and theta. There's only one of them that can change. H stays the same, m stays the same, c stays the same. The only one that can change is theta. So here's what I want to do. If I want this number right here to be as big as possible, I want this number to be as big as possible. That make sense? H over MC isn't going to change. So the number inside the brackets has to be as big as possible. Let's figure out what theta will produce a number inside that red circle as big as possible. I want to try a few different angles. I don't need to try all of them. 74.2, who cares? Okay, what angles do you think I should try here? What are the important ones to give a shot to give a try to? Yeah, John? Okay, 0, 45, let's say 90. Okay, maybe let's say 180, even 270. Good. And you could even try like say 135 or something like that. But I think you're going to find that if you're trying these ones, I think you're going to get what you need here. Okay, let's say cosine 0. What's cosine 0? We're going to try that on your calculators. Cosine 0. 1. Okay, some of you remember that. Good. If you remember that, that's fantastic. If you don't, just do it on your calculator. What's cosine 45? 0.707, I think, isn't it, John? Okay, what's cos 90? 0. Cos 180? -1, I think, isn't it? Cos 270, I think, is 0 as well. All right. What's 1 minus 1? 1 minus cosine 0, 1 minus 1 is 0. Okay, if inside that bracket is 0, then h over mc, whatever that is, times 0 is 0. Delta lambda there would give me a value of 0, right? Well, that's not the biggest change in wavelength. That's the smallest change in wavelength. You ever get a question that says this, what's the smallest change in wavelength that you can get? It's 0. And it occurs when there's a scattering angle of 0 degrees. What about 45? Well, 1 minus 0.707 is about 0.3. About 0.3 times that value is, I'm not sure. Let's just say 0.3 times whatever h over mc is, okay? Roughly. Cosine 90, 1 minus 0 is 1, okay? 1 times whatever h over mc is. Right now we can get rid of these, right? Those don't produce the maximum possible change in wavelengths because this is clearly bigger than these two. 1 times h over mc is bigger than 0.3 times that, or it's bigger than 0 times that. What about minus 1? 1 minus -1 gives me 2. 2 times h over mc. Oh, that's our new maximum value, right? 2 times whatever h over mc is. 270, 1 minus 0 is 1. 1 times h over mc is 1 times the value of whatever that h over mc is. Okay, that disappears. Here we are. The angle is 180 degrees. So let's say 6.63 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 times 3 times 10 to the 8. 1 minus cosine 180. So it ends up being this times 2, which I think works out to be 4.4 or something like that, times 10 to the minus 12, if I remember. Kate, do you have that there? Thank you, Parker. We get 4.85 times 10 to the minus 12 meters. That's our biggest possible change in wavelength, because there's no other angle besides 180 that will produce a number inside those brackets that's 2 or more. 180 produces the maximum value inside the red circle, therefore the maximum value of delta lambda. Is that okay? Now, there's not really any practice questions to go along with this one, because it's pretty much a standalone question, right? What else could I ask you with this besides, look, you got the maximum wavelength. Every question you see that asks you for the maximum wavelength is going to give you the same answer. It is not dependent on the initial wavelength. It doesn't matter. Delta lambda is delta lambda. I don't know if you ever see this on a test. Okay, if you did, hey, get lucky. We went over that question in class. If you don't see this on a test, okay, that's fine. We're smarter because we've gone over it. Hey, but if you do see it over on a test, listen, don't memorize that number, 4.85, even though it's going to be the same every time. Don't memorize it. Don't even necessarily memorize the angle that produces it as 180. Just remember, oh, I remember we tried a bunch of different angles, and I found out what cos theta was and figured out which angle would produce the biggest delta lambda, and then figure it out. Okay, don't memorize any more than you have to here. Just figure it out. Just remember how to figure it out, that's all. I'm going to give you some questions here, not to work on in class, not even assigned as formal homework, but just if you're looking for more questions to work on the Compton Effect as practice, page 725, number 1 to 7 will work for you. Clearly, we won't go over them in class tomorrow, given that tomorrow is test day. But you guys have class after lunch tomorrow, which gives you an opportunity, if you have any questions about this or anything else, to pop in at lunchtime and ask me those questions before you start writing the test. Last topic of the unit, which is going to take us about 3 or 4 minutes. Think back to the first day of this unit. We talked about Maxwell's theory of electromagnetic radiation, right? The changing electric field, the changing magnetic field, the accelerating charged particles, and so on. We established that there was 4 properties of waves that were exhibited by EMR, which showed or provided evidence for the wave nature of EMR. So electromagnetic radiation, light of any kind, radio waves, microwaves, infrared, and so on, they're all waves. It's only been the last week or so that we've started talking about the particle nature of light, the particle nature of electromagnetic radiation. And that started with Einstein and this photon theory, right? Post-20th century physics. Post-Einstein. We've got the wave nature of light. We've got the particle nature of light. Now we say, we call it maybe the wave-particle duality. Light exhibits both properties of waves and properties of particles. It's not a wave, it's not a particle, it's both. It's a wave/particle, all at the same time. We've also said in physics this year that physics is a very symmetrical subject. If A will cause B, then B will often cause A. Or if there's a relationship between A and B, then there's often a similar relationship or a complementary relationship between B and A. A guy named Louis de Broglie, it's pronounced de Broglie, but it's spelled de Broglie. A guy named Louis de Broglie proposed an argument, a hypothesis, purely based on that symmetry. A causes B, or there's a relationship between A and B, there's a complementary relationship between B and A. De Broglie said that if waves, like EMR, have particle properties, right? Waves have particle properties. And we've established that with the photoelectric effect and the Compton effect. Waves do have particle properties. Then maybe particles have wave properties. Particles are like electrons or protons or baseballs have wave properties. Now, as it turns out, the mass of a baseball is much too great to exhibit any real wave properties. Okay, but theoretically, we'd say that anything of mass has a wave nature. Electrons, hey, mass of an electron is pretty small. Maybe we can observe the wave nature of an electron. Now, even though de Broglie didn't have any evidence to support his hypothesis that particles like electrons have a wave nature, even though he didn't have any evidence to support that, he derived an equation for the wavelength of an electron, the wavelength of a proton, the wavelength of a baseball. We don't need to know that equation. Occasionally, you do see it on an exam, but when you do use it on an exam, they give it to you and they provide you with context and explanation for it. Sometimes we've seen that on exams before, right? Where we have an equation that we've never seen before, but they just give us some information around it. They explain it to us. If you ever need to use that equation, they'll give it to you and they'll explain it. So we won't do that right now. He derived an equation for the wavelength, even though there was no proof to even suggest there was a wavelength. It was just an argument based on symmetry. Now, do we have evidence now to prove what de Broglie said? Yes, we do. We have a lot of it now. Evidence to support de Broglie's hypothesis came through electron diffraction experiments. What do we mean by that? Well, we talked about diffraction of light. Diffraction and interference. When light goes through an opening, it spreads out, it diffracts. When light goes through two openings, it spreads out through the two openings, diffracts, interferes, and produces bright spot, dark spot, bright spot, dark spot. We get an interference pattern. Oddly, when electrons go through two openings, we also see an interference pattern. Interference is a property of waves. So if we see this interference pattern with electrons, that's evidence to suggest that electrons do exhibit a wave nature.